off. It'd been cool if I would have been recording before. So let me just reiterate here that this week we're going to do binary trees and binary search trees today. We're going to do, I can look in the book, so I'll get it right this time. I think the next thing we're going to do, let me find it, is going to be the AVL trees or the self-balancing trees. And then we'll do the B trees, be the last thing we do. And that should get us up through Thursday. Thursday should be just review and any other spare topics. Problem set will go out today. I've just now got onto Moodle again. So it'll go out later today, and it'll have just a couple of problems, no more than one per each type of problem. And those will be due on Thursday, okay? So I can take a look at it before the exam. I'm going to finish up grading everything else that's out there. I graded some of it, but then people hadn't turned it in yet. So get stuff turned in quick if you can. I'm still not sure when I have to have grades in, but I fear it's probably Monday. So there's not a lot of time after class starts or after class is over in order to get more stuff in. Okay. Okay, so let's see. Okay, so why'd it go away? Did it go away? There it is. I assume you guys can see that. So we're talking about binary trees this time. Okay, so the binary trees, what we're trying to get at, okay, when we look at the things that we have done so far, okay, again, this class is called data structures. Okay, it's a way to organize our data. Okay, and we want to be able to do things like insertion, deletion, and lookups or searches. Too many O's there. Relatively fast. Okay, so that's kind of what our goal has been. We also want efficiency if we can get it. Okay. So far we've talked about arrays, and arrays have random access. So if it's sorted, if you maintain it being sorted, then we can do a binary search. It's pretty efficient, right? If it's unsorted, you're stuck with a sequential search, which is not good at all. Okay, which only works in very small cases. Okay, so that could be an issue for sure. We also have the issue we've talked about several times, that with an array you have to allocate a block of memory that can't grow. Okay, so the other data structures we've talked about, things like a linked list, where again we have random points in memory, random nodes that we're able to point between. Okay, depending on the data, if we only need linear access to data, that could be a very good thing. They're very efficient with memory. Okay, but when it comes to searching, our only shot on a regular linked list is going to be a sequential search. You have no way. All you see, all that a linked list presents to itself is that. Okay, so searching is not going to be efficient. Okay, adding to the linked list is relatively straightforward. So that's not too bad. Deletions aren't too bad. And again, they're very efficient, but they're not quick when it comes to searches. Okay, when we have our stacks, which we tend to draw like this, again, they're a more specialized way of doing things. Okay, where we have the last in becomes the first out. So this is the first one to pop out. And again, this is all you see. Okay. And the same thing with queues, which we tend to draw vertically, where this is all you can see. They're not made to be sorted. They're not made to be searched. They're made to process linearly. So they're basically just the same idea as a linked list. Okay, so they're not the general purpose kind of data structure. They're made for specific problems. Okay, so it gets us to this idea of a binary tree. Okay, so the binary tree is going to allow us some more flexibility. Okay, so let's start with the definition, and then we can see what it's going to look like visually. So I'm on page 600 if you're keeping track, at least in my book. Okay, so a binary tree okay, so we're going to say binary tree T is either empty or the following are hold. One, T is going to have, so it has a special node called the root node. Okay. And we have T has two sets of nodes, which we're going to call LT, so the left subtree of T, and RT, the right subtree, such that LT and RT are also binary trees. Okay, so this is a recursive definition. We're going to see this, that every tree has two subnodes, which are also trees, or two nodes, the left subtree and right subtree. Okay, so when we look at these visually, so again, trees generically are going to have this kind of a structure with one root node going down to all the child nodes, which can again have more children. But with this binary, we're saying that there's one, we're going to call the root. We have one, then that can be the left subtree, and we have one that is the right subtree. Okay, so there are no other branches or edges off of root. Okay, every node has exactly two. Okay, so when we're looking at coding, then if you look kind of like a linked list, we're going to have still, so visually we can do it this way. We're going to have whatever our info is, okay, and then we're going to have basically a left and a right pointers that come off of that. Okay, but we tend to draw them just more like this. You have, here's our root node, and then we have a connection to B. Over here we have a connection to C, and then we can have further nodes from there, as many as you want. Okay, so that's the basic idea behind the tree here. Okay, when we talk about binary trees, we can have different number of nodes. They don't have to make any sense. We can have, in this case, we've got the left subtree, so the LT of A has 3 nodes, where the RT only has 1. So there's no idea. I mean, you can have something that looks like this, and that's still a binary tree. Still does not violate the rules. Okay, so there's no sense of any kind of a balance. Okay, so when we go to start coding this up, we're going to create a struct that looks like this. Okay, so we always do our templating. So we have template, class. They're going with elem type this time. Remember, it doesn't matter what you call it. We do a struct, binary tree node, and it's going to take the elem type info. It's going to have a binary tree node, again, the recursive part of this, on elem type, called L-link, and another binary tree node, elem type pointer, called R-link. Okay, that's the basic structure we're going with. So again, like I did a second ago, we're going to have the info up here. We have an L-link pointer here and an R-link pointer there, which point off to something. Okay. So again, we talk about if we have this kind of situation, that A is the parent of B and C, and B is a child of A, and so forth. Okay, so the basic ideas that we have there. Okay, and we tend to draw them this way just for simplicity, but know that everyone just has two. That's what they're called. So we have a few more terms that we need to deal with here. Okay, a node in a binary tree is called a leaf if it has no left or right children. Okay, so we have A, comes down to B, comes down to C. Those are arrows. They only go one direction. And again, in kind of what we were doing before, all that's visible to the outside world typically is this root node. And these, I'm putting these in order, but there's no implied order at all. And this can be anywhere. And it can be whatever. We could have X off of there if we wanted. Okay. So if you're looking at this for a leaf node, again, to identify those, D is a leaf node. It has no children. X is a leaf node. H is a leaf node. And G is a leaf node. Okay. We also talk about the level of a node. It's going to be the number of branches on the path from the root to the node. Okay. So the level of F is going to be 1, 2. Okay. Okay. We can also talk about the height of the tree is going to be the number of nodes on the longest path from a root to a leaf. Okay. So in this case, we have a couple of times. We go 1, 2, 3. We also go 1, 2, 3 here. Okay. The others are going to be 1, 2, 1, 2. So in this case, the answer is 3 for that. That's the height. Okay. So let's see what else we've got here. There's some definitions on the height and how that works. Okay. Again, you're always starting up at the root, and you have to kind of calculate by going down and seeing what you find. Okay. There's another on page 604. It gives us this idea of a copy tree function. We have the same issues that we've had before with the deep copying, that if we have a tree that, I mean, what this really looks like, if we have our memory, we would have the root here, and let's say left child, right child. Okay. And this is tree A. If I would say tree B is equal to A, then both A and B would point to exactly the same location. You'd have a shallow copy, and then if you change A, you change B, and it hasn't done you any good at all. Okay. So if you want to actually make a deep copy, it's similar to things we've done for other structures, and that's there on page 604 and 605. Okay. Notice these are all going to be recursive. Algorithms. Okay. Which we've seen that before as well. Okay. And if there are questions along the way, stop me, let me know. So let's go on to the next part then. Binary tree traversals are important. With those, it comes down, you've got a binary tree of some sort. Can't have two of the same name. So we've got this. Okay. So it's all the traversal. Again, we're always starting at A. But we have two things we can do. We can either visit the node, which means we add the content of that node to our list that we're creating of all the nodes, or we can move right or left. Okay. And it gives us the three different ways to do things. So if we have an in order traversal, okay? It's going to be go left, then visit, and then go right, okay? So for this particular tree, it means from A, we'll go, again, these are a recursive call. We're going to go left to B. We start over again, go left again to D, and then we go left again to G, okay? So in this inner order traversal, the set we're going to create is going to be G is going to happen first, okay? Note that if these were, these are a binary search tree, which we're going to get to in a minute, then that's the smallest position in the tree, okay? So at G, we tried to go left, we couldn't. So we visited, we tried to go right, and we couldn't. So we go back up a level. That recursive call stops, okay? We go back to D, okay? We've done left, we can't go left again, so now we're going to add D to the list. We try right, there is no right, so then we go back up to B. We've already done the left there, so now we do the visit, get to B, okay? And now we go to the E node, okay? Again, it's a new recursive call. We're going to try to go left, can't, visit, so the E comes in there. Try to go right, there's nothing. Gets us all the way back to A. So now we're at A, okay? A has gone left, A has visited, A now goes right to C. At C, we go left and get to F. F, we try left, can't do it. Okay, then we visit, then we go right, nothing. We come back to C, and now we're done. Okay, so that is an in order traversal of this list. Okay, and the other traversals just vary the order of steps you do things in. Okay, so with the other one, the next one's a pre-order, and I won't go through all these, they're in the book. Pre-order is going to do a visit first, then it's going to do a left, and then it's going to do a right. Okay, so this would start out with A being the first thing, A, and then go to B, and it would visit B, okay, and so forth. Okay, and then the last one is the post order, which does left. It's the only other option here, a left, right, and then visit. Okay. Under this scheme, A becomes the last one you visit. Okay. So the in order A is in the middle, again, assuming equal number of nodes each side. Pre-order A is first, post-order A is last. Okay. And this doesn't make a lot of sense with an unordered list, but we're going to get to ordered list in just a second. Are there questions about any of that stuff, the traversals? You'll see that off and on throughout your computer science careers. Okay. Some big examples through there on the other parts of things. Okay. So what the book does, and I'm going to have you do something differently. The book starts off on this section on implementing binary trees. And it creates this class binary tree type. Okay. Well, it's going to, where it defines the node, it's going to go through and do some other things. Okay. But then it's going to say, basically, it says here in the middle of page 609, other than for the search, insertion, and deletion operations, it doesn't define those, okay, in the binary tree. Okay. It's because insertion and deletion are problematic somewhat in an unordered tree. Okay. So if we have an A and we have a B and we have a C, if I'm going to insert a new node, where's it going to go? I mean, you can define rules for that, but there's no natural way to do that. And if we delete a node, how do we connect it back up? So you have to be a little more arbitrary, okay? And it turns out that just plain binary trees are not used particularly all that often, okay? That what we tend to use instead is a binary search tree. Oh, one thing I want to say before we go on. Notice here we're doing left and then right. You could do right then left if you wanted, but it's just not a thing. I mean, it would create its own traversals, but I don't think that really even has a name. Maybe it has, maybe it's reverse in order traversal, maybe, but we just don't tend to do that. Okay, so I sometimes get that question. Okay, so searching then just becomes, you got to search everywhere. There's no good way to do it. Okay, so the book implements that except for those features, and you can go through that if you want. But what I want you to do, let's talk about binary search trees first, because what they do after they get that working is go with the idea of a binary search tree. Okay. So with the binary search tree T is either empty, I'm on page 617, is either empty or the following is true. It should be R true, but you get the idea. Okay, 1, we have a root node like before. Okay. 2 is the same as well. So it has the LT and RT, that hasn't changed. Okay. What changes starts in 3, and it's that the key in the root node is larger than every key in the left subtree or in LT, and smaller than every key in RT. Okay, and that's the important part. That's what differentiates. And then the 4 is now what the 3 was, that LT and RT are both, in this case, binary search trees. Okay, so again, we've added the word search here. Okay, and this is the real, this is what makes it the search part. It's this ordering. Okay, so it's a binary tree in many ways. So the other operations that we normally do, such as finding the height of the tree, the number of nodes, the number of leaves, traversing the tree, copying the tree, those are exactly the same as they are for a binary tree. So again, binary tree is unordered, binary search tree is ordered. Okay, but the other things we're going to do here, we're going to be able to search very easily through a binary search tree, and we're going to be able to insert an item and delete an item in ways that make sense. Okay, so let's look at this. We'll put some numbers for the nodes instead of letters, make it a little easier. So let's say we have 25 as our root node. Okay, if I need to insert the following: 15, 4, 31, and 17. Okay, with 25, I'll make that a little clearer, as our root node. When I go to insert 15, before I could insert anywhere. Now there's only one place it could be. 15 has to be in the left tree because the key value 25 is bigger than everything in the left tree. Okay, so it's going to go here. I'm going to add the 15 here. Okay, so we got that one done. When I'm going to add the 4, again, all that I see, all it's outward facing is the root. I'm going to go from the root 25. 4 is going to be down the left subtree of 25. I go to 15. Okay, 4 is going to be on the left child of 15. Okay, gets me to here. No question where that's going to go. Okay, 31 is going to go in the right subtree since it's bigger. Okay, 17, it needs to be here because it's less than 25, but it's bigger than here, so it's going to go to the right tree to get to 17. Okay, that is the only tree that I could have made, the only binary search tree. Okay, and again, when we look at the height is 2. Okay, that's the path. The longest path is 2, the height of this tree. Okay, has 5 nodes. And the What else? 15 is also a binary search tree. Okay, and 31 and 4 and 17 don't have any children. And the leaf nodes are 4, 17, and 31. Okay, so once you have this is a binary tree, and we can do our in order or whatever. But again, note, as I was saying before, on an in order traversal, which is left visit right, okay, we're going to, and let's just do the
Does
call.
order matter with these?
Order absolutely matters. That's what I'm saying. You have to, well, relative order, okay, in that the left is always smaller, the right's always bigger. Okay.
So say if you were to add 18, 19, and 20 to that tree above,
Yes.
like the order you add them would change the shape of the tree, right?
It would. Yes. So where's 18 going to go? 18 is it's smaller than this, so it goes here. It's bigger than this, so it goes here. It's bigger than this, so it would be in the right tree. Okay.
But now if you were to add 19, it would,
yeah. It gets ugly quick, which is why we have the self-balancing trees we'll talk about. Okay. So again, all we don't know the absolute ordering of everything, but look what we can do here because of the ordering. Okay, so if I do the in order traversal, let's look at this first call from root. Okay, so I'm at the 25 node. Okay, it wants me to go left. That's not a left. It wants me to go left. It wants me to visit. It wants me to go right. Okay, I go left to 15. So now this starts with my own. So I've done that. I've got a left, visit, right there as well. Okay. I have a left option. I go to 4. These are recursive calls, so they're all on the stack. So I've done that. Okay. At 4, I do try this, can't do it. I visit. So 4 is my first output. Okay. And then I go right. There's no right. Okay. So that goes away. We've dealt with this. Okay. So now I'm back to 15. I did the left. Now I do the visit. 15. Now I do the right, which opens up a new block for 17 here, which has its left, right, visit. Okay, and I've done that now. Okay. I can't do a left, so I do a visit. Can't do a right. No, I had that in the right order, wrong order. Visit, right. I do the visit. I do the right. There's nothing there. This goes away. Okay. I'm back to 15. We're done. We've done everything we can. That goes away. Now I'm back to 25. Okay, on the original call. I've done the left, so now I do the visit. Okay, so now I do the right. At the right, I go to 31. I do a left, visit, right. No left, I do a visit, do the 31 there. No right, this goes away. That's been done. The whole thing goes away. Okay, and what we have here is ordered or sorted. Okay. Okay. So no matter what order they get in, the in order traversal is going to produce a list of ordered bits, basically. Okay. And then the post order is going to do a different ordering where the root ends up being the very last thing, and then the pre-order, whichever pre-order, ends up with the root being the first. And those have different things you do. But the in order is probably the most common because it returns back a sorted list. Okay. So the insertions are relatively straightforward. We can do the ordering or the traversals as we did before, not a big deal. With the deletions, we at least have something to go on here. Okay, if we're going to delete a leaf node, it's never a big deal. But let's say we're going to delete 15. Okay, then we just have to figure out how to move things. So if 15 goes away, we have to promote one of them. The only one we can promote is 17 and have it still be a binary tree. So we don't have to worry about those decisions. So it simplifies how we can make those things work. Okay. And then the searching is going to be a piece of cake as well. Okay. So with the search, we're doing basically a binary search every time. Okay. So again, we could have this massive structure of trees. And if it's a binary search tree, there could be thousands here, wouldn't matter. It's all the same. All we can see right now is this. So we're here. And we're going to say, is this key term equal to what we're looking for? If so, we found it. If not, is the key we're looking for bigger or smaller? Okay. If the key were, so let's say this is a 20 and we're looking for 100. So our K is 100. Okay. This isn't it, so I can get rid of that. But guess what? None of this left tree is it. Got rid of all of it. Okay. So now I can move to here. Say this is a 50. Okay. I know again that this and its whole left subtree are gone. Okay. So just like we did with arrays, by doing a search, a binary search on a binary search tree, if we have a balanced tree, we're getting rid of half of the elements every time. Okay. Again, because if we're looking, for example, for 100 in this tree up here, okay, I know it has to be to the right of 25 because it's a binary search tree. I go to 31, it's not 31. I know 100 is not there. I never even have to look at the 15, the 4, and 17. Okay, and these are baby examples. Ramp this up to thousands or millions of data points, then you can see the advantage of this. You can find things very quickly. Okay, so it's the reason that we do that. Okay, and then the book goes through and gives you the code for the searching. And then we talk about the deleting. We just have to make sure we reroute things properly. Okay. And I think, yeah, it talks about the binary search tree analysis. And it turns out that, as I said, if we have a balanced tree with relatively the same number, then the search is going to be a log 2n or a log n, okay? Because it deletes half every time, okay? But that's the average case or the best case. The worst case is that it's something like this, and it turns out a search, that's a big O of log n. The search is going to be a big O of just n. It's linear. You still have to go through everything, okay? So that's why we're going to talk about the balanced search trees later, okay? Then that's on page 627 and 628, okay? It also gives a non-recursive binary tree traversal algorithm. I don't care too much about that, so I wouldn't worry about any of those non-recursive ones. Okay. And I think that's where we're going to stop today as far as the material goes. Okay. Because the next thing we're going to get into are the self-balancing trees, of which there are several. We'll cover that tomorrow. Okay. So what I want you to work on today until 2 o'clock is that I want you to implement a binary search tree class. Okay. And call it binary search tree .h, or yeah, I guess it would be .h. Yeah. Okay. So not the book again has a separate binary tree and then adds on and inherits for a binary search tree. I just want you to do it all in one. Okay. So yours is going to be by default a binary search tree. Okay. So most of the coding's in the book. So start with the binary tree stuff. And then instead of inheriting, just go ahead and add the functionality for the insert, delete, and search into your one class that you have. Okay. So all of those functions need to be implemented. So again, you start with, you have to have the constructor. Okay. Because it has pointer data, you have to make sure you're overriding or overloading the assignment operator. You have to have a copy constructor. You have to have a destructor, all those things we normally do. Okay. So you need to put all that stuff in. but you'll also need the insert, delete, search, the traversals. Okay, I think that's about it. There may be a couple others, but whatever the book does. So go ahead and implement those into your new class. Okay, and then write a test program. And this will be the first homework problem on the problem set, but I want you to go ahead and work on it now. And if you have questions when we come back at 2 o'clock, I will answer those questions for you. Okay, any questions right now? Okay. Okay, so then we'll stop for now, and I will fire up the Zoom again at 2 o'clock, and we'll be able to go through that and see what you're having trouble with. Okay, and I'll try to get the rest of the problem set for the week up, since I now have access to the internet, to Moodle. Okay, see you at 2 o'clock then.